Hey Math 135, what's up? In this video we're going to be looking at some extra problems from section 7.6 on Bayes Theorem. And number one, we have a Venn diagram. This is an experiment with three mutually exclusive events, A, B, and C, that form a partition of our sample space S. I guess we can label our sample space here. And then we also have an event D as well. In part A, if we want to find the probability of event A, consists of two pieces. There's the part of A that happens with D, and the part of A that happens with D complement. Now, if you add up all the numbers in the Venn diagram here, they add up to 100. And so if we want to, instead of thinking about these as counts, want to think about these as probabilities, we can just put decimals in front of all these. Because again, we're effectively dividing by 100 for the probabilities here. So the probability of A with D is 0.20, and the probability of A and D complement is 0.25. So the probability of A is 0.45. For the probability of D, we can do something similar. That will be the probability that D happens with A plus the probability that D happens with B plus the probability that D happens with C. And these are mutually exclusive events, which is why we can just add these probabilities together these are mutually exclusive events. So we can use the easier addition formula here. So it's 0.2 plus 0.15 plus 0.10. And that gives 0.45 as well. The probability of D given A, we can use our basic conditional probability formula. That would be the probability of D and A divided by the probability of A. The probability of D and A is 0.20. That's this event right here. The probability of A we found in part A to be 0.45. And then if we do 0.2 divided by 0.45 on the calculator, you get an answer rounded to 4 decimal places of 0.4444. All right, in part D, if we want to find the probability of A given D, we can again use the basic conditional probability formula here. Except for now we're dividing by the probability of D. D is the conditional event in this case. The probability of D and A is 0.2. The probability of D we found in part B was also 0.45, and so this will also end up being 0.4444. In E, we're asking, are A and D independent? And there's a couple of ways of answering this question. There's the test for independence that asks, is the probability of A and D equal to the probability of A times the probability of D? If the answer to that question is yes, then they're independent. So let's look at that. Probability of A and D is 0.2. We've used that a few times now. Is that going to be equal to the probability of A, which is 0.45, times the probability of D, which is also 0.45? When you work out 0.45 times 0.45 on your calculator, you'll get a number that is not exactly 0.2. So these two values are not equal, and so we can say no that way. You can also, so that's the test for independence. That's what our book calls it. You can also ask, is the probability of D given A equal to the probability of D? And the probability of A given D equal to the probability of A. Remember, that's our definition for independent events. This is basically saying if the probability of D given A is the same as the probability of D, that basically means that D doesn't really care whether or not A happens. That's our intuition behind independence. And let's see, the probability of D given A is 0.444, and the probability of D by itself is 0.45. So these two aren't equal. Same thing for those two. So that's another way. That's another way to see if events are independent. Are A and D mutually exclusive? Now this is a different question. Remember, independent is not the same as mutually exclusive. All right, mutually exclusive, we're asking, is A intersect D empty? And since the probability of A intersect D is non-zero, then it can't be empty. So the answer here is also no. These events are non-empty. Actually, we can see from the Venn diagram that there is some overlap between the events A and D. So again, there can be some confusion about the distinction between independent events and mutually exclusive events. Make sure that you understand the difference. Or at least realize that there is a difference and know how to deal with each individual case. You don't necessarily have to have a perfect understanding of what the difference is, but make sure that you understand that there is a difference and be able to deal with the difference. All right, the probability of D complement. There's a couple ways that we could handle this. We could do the probability that D complement happens with A plus the probability that D complement happens with B plus the probability that D complement happens with C. That's because we have a partition. A, B, and C are a partition. That's why we're able to do this. Since A, B, and C are mutually exclusive, all these intersections are also mutually exclusive, and they form a partition of D complement. So if we look, these are the values for A and D complement, B and D complement, and C and D complement. So 0.25 plus 0.10 plus 0.2. And that gives us 0.55. So that's one strategy for finding the probability of D complement. We also could have used a complement strategy here as well. So that the probability of D complement is 1 minus the probability of D, which is 1 minus the 0.45 that we found in part B. That also would have given us 0.55. H, we have the probability of D complement given A using a basic conditional probability formula. That would be the probability that A and D complement happens divided by the probability of A. A is our conditional event here. Probability of A and D complement, we wrote down in the previous problem here, 0.25. And the probability of A from very early on was 0.45. And on the calculator, this rounds to about 0.5556. Now, one thing that you can notice here is there's actually a complement formula for conditional events. The probability of D complement given A is equal to 1 minus the probability of D given A. It's basically the same as our regular complement formula, except for we've changed both of these to be conditional probabilities with the same conditional event. So if you want to memorize a new complement formula, you can do that. Remember, this complement formula is one that's going to be given, but if you want to memorize a second one, you can do that. It can be helpful. It's actually something that we use somewhat regularly. In part I here, the probability of A given D complement, that would again be the probability of A and D complement divided by, in this case, the probability of D complement. So 0.25 divided by, let's see, the probability of D complement we found up here, 0.55. And that works out to be 0.4545. And so based on the fact that we have this new complement formula, maybe there's a new complement formula here. Probability of A given D complement, is that the same as the, 1 minus the probability of A given D? If I have conditional events that are complement, does it work out that way? And unfortunately, it doesn't. If we go look at the probability of A given D and the probability of A given D complement, these two values don't add up to 1. So that doesn't work. That one does not work. All right, that'll do it for problem number 1. Moving on to problem number 2. We have a tree diagram for a 2-stage experiment where there's 3 things that can happen in the first stage and 2 things that can happen in the second stage. We want to complete this diagram. So remember, in the first stage, all the probabilities in the first stage had to add up to 1. So whatever this unknown probability is, right here, that's actually the probability of C. It's going to be 1 minus 1/5 minus 1/3. Now 1/5 plus 1/3, 1/5 plus 1/3 is 3/15 plus 5/15 gives you 8/15. So this is 1 minus 8/15, which is 7/15. Or if you're handy with your calculator, you can do the work on your calculator and tell your calculator to convert it back to a fraction. 7/15. All right, on to the second stage things. Now remember, this 1/4 is the probability of E given A. And we just talked about the second number here, the probability of E complement given A. These things have to add up to 1. We just kind of talked about that fact right up here. So this number right here has to be 3/4. Our probability, this right here is the probability of E given B, is going to be 7/9, because these two values have to add up to 1. And then finally, this last second stage branch down here, probability of E complement given C is going to be 4/7. All right. Now there's also this rightmost column that we can fill in. I'm going to give myself a little bit more space here. Get rid of some of this unnecessary stuff. The right-hand column of these trees we get by multiplying down the branch. So here we get 1/5 times 1/4. That gives 1/20. Down the second branch, 1/5 times 3/4 gives 3/20. The third branch down, B and B then E, would be 1/3 times 7/9 would give 7/27. That would be, again, these probabilities are intersections, the probability that B and E happens here. B and E complement be 1/3 times 2/9, which gives 2/27. And then the last two here, 7/15 times 3/7 would give 3/15, or 1/5 if you like to reduce these fractions. And the very last one there, 7/15 times 4/7 gives 4/15, which can't be reduced. All right, so in part A here, when we want to find the probability of E, well, E happens three ways. We got B and E right here. A and E is the very top path, and then C and E would be this value right here. So since we have a partition of our first stage, we kind of have a partition of the E event. That would be the probability that E happens with A, plus the probability that E happens with B, plus the probability that E happens with C. That'll be 1/20th plus 7/27 plus 1/5. Now I will go ahead and do this on the calculator. Again, I'm just adding these fractions together, typing it in as I see it here. And then once my calculator gives me a garbage decimal answer, I use the fraction to decimal feature of my calculator to get an answer of 55/108. All right, on to part B then. For the probability of C given E, we can use our basic probability formula. Sorry, the basic conditional probability formula. That'd be the probability that C and E happens divided by the probability of our conditional event E in this case. Probability of C and E was 1/5 from up here. And the probability of E is what we just found, 55/108. Using some facts about division of fractions, 1/5 divided by 55/108 is the same thing as 1/5 times the reciprocal of that, 108/55. All right, and then when we multiply these fractions together, you should get 108 divided by 275. On to part C, the probability of E complement. There are, again, a couple ways of getting the job done. I think the easiest way is to just use the complement formula. So that'd be 1 minus 55/108. Which will be 53/108. You could have also looked at all of the events up here, this partition for, sorry, this should be A and E. The probability of A and E complement, the probability of B and E complement, the probability of C and E complement. You could have taken those and added them together, 3/20ths plus 2/27ths plus 4/15. You should get the same answer, 53/108. And we can use that when we go to find the probability of B given E complement using the conditional probability formula. That would be the probability that B and E complement happens divided by the probability of E complement. B and E complement, that was 2/27ths from up here. The probability of E complement we just found in part C. Again, using some facts about fraction division, this will be the same as 2 over 27 times 108 over 53. And then 108 is actually divisible by 27, so this ends up being 8 over 53. All right. On to number 3. A medical test has been designed to detect the presence of a certain disease among people who have the disease. The probability that the disease will be detected by the test is 0.97. However, the probability that the test will erroneously indicate the presence of the disease in those who do not actually have it is 0.05. It's estimated that 6% of the population who takes the test will have this disease. They're going to ask us a couple of probability questions here, and I think making some trees is the best way to deal with them. Now, since they gave us the probability of having the disease, that's the thing that we want to make our first stage here. Either the person has the disease or they don't. I'm just going to call that D complement. And when it says 6% of the population had the disease, that means there's a 0.06 probability that the person taking the test has the disease. And that leaves a 0.94 probability that they don't. Now, in part A, I guess for the person who takes the disease, there's two things that can happen. Either they get a positive test or a negative test. Same thing for the person who doesn't have the disease. In part A, it says if the test administered to an individual is positive, that's our conditional event. So we're doing a conditional probability given that the test is positive. Hopefully the P for probability and the P for positive test aren't super confusing. All right, let's just change that then. Let's avoid the confusion. We don't have to use letters for all these things. We could use plus and a minus for positive and negative. Plus, minus, plus, minus. All right, so our positive test is our conditional event. What is the probability that the person actually has the disease? So they're asking, what's the probability that our person is diseased given they get a positive test? And the conditional probability formula here says that will correspond to the probability that they have the disease and have a positive test all over the probability that they get a positive test. So we're just focused on the positive test stuff. We're not going to fill in this entire tree diagram. We're just focused on the positive test. All right, so for the person who has the disease, it says here the probability that the disease will be detected, that's a positive test. So the probability that our diseased person is going to get a positive test is 0.97. And so if we want to know the probability that a person is diseased and gets a positive test, we can multiply those together. 0.06 times 0.97 gives 0.0582. And then for, since we are interested in all of the positive results, the probability of a positive result from a disease-free person, let's see. The story says that the test will erroneously indicate the presence, so there's going to be an incorrect positive result. This is called a false positive. That probability is 0.05. So if I take 0.94 times 0.05, that gives me 0.047. So if I just pick a random person taking this test, the probability that that person has a disease and gets a positive test is only slightly larger than the probability that the person doesn't have the disease and still gets a positive test. Well, that's just because there's so many more people who don't have the disease here. Kind of makes this result a little bit unintuitive. Anyways, when we go to finish this computation, we get the probability that the person has the disease and gets a positive test, 0.0582 on top, and then the probability that a person gets a positive test. Well, these are the two ways that can happen. Those are mutually exclusive events, and so we can add those things together to get the probability of a positive result. And when you work it all out on the calculator, 0.0582 divided by, make sure when you enter this on your calculator that you're getting this denominator in parentheses on your calculator. If you have one that doesn't show you a fraction, some calculators allow you to type in a fraction that looks like a fraction. Mine doesn't. So I got to be careful to get those parentheses in there, respect the order of operations. And this is approximately 0.5532. So again, it seems like this test is accurate. It seems like this test is pretty accurate. However, if you get a positive result, it's only slightly better than a 50-50 probability that you actually have the disease. Again, it's an unintuitive result here for this conditional probability. In B, we're looking at taking the test twice. All right. And assuming that the test is positive both times. So there's a conditional event here. We're taking the test twice and getting a positive test both times. We want to know, again, the probability that the person actually has the disease. And we're going to assume that the tests are independent. All right, so we got another tree here. And the first part of this tree would look the same as our tree from before. We have disease and disease-free, 0.06, 0.94, because again, 6% of the people taking this test have the disease. And then we have a positive and a negative result here. Now we're just focused on the people who get a positive result twice. So there's a second test where the results of the second test can also be positive or negative. Because again, this test isn't 100% accurate. It might give you different results. But it's the same test, and there's some independence here. I guess in the real world, it might be the case that, you know, if you get a false positive on the first round, then there's something in your biochemistry that will increase the odds of you getting a false positive the next time around. We're not going to consider that case. We're just going to say that the tests are independent here. So there's a 97% chance that the diseased person gets a positive result on the first test and as well on a second test. 97% chance that they'll get a positive result on the second test. For the person who doesn't have the disease, there's a 5% chance that they get a false positive result in the first round and the same chance in the second round. That's what it means for these to be independent. I guess, I don't want to write it out because it's more confusing than it's worth. The idea here is that this probability doesn't change from that probability. So, I guess the question that we're asking here is, what is the probability that the person has the disease given they got 2 positive test results? So that would be the probability of the disease and 2 positive test results divided by the probability of having 2 positive test results. All right, if we multiply across the top here, the point go 0.06 times 0.97 times 0.97. We get a probability here of 0.97 0, 5, 6, 5. I guess I'll round it to 4 decimal places. That is the probability that a person has a disease and gets 2 positive tests, so that's our numerator. It's also one piece of our denominator. The other piece of our denominator is when I take the 0.94 times the 0.05 times 0.05. And that gives us 0.0024 when I round to 4 decimal places. All right, then finally, if I finish off this computation, some of the calculator work here is a little bit annoying, but I think it's important to see what the answers are in some of these unintuitive ones, or some of these conditional probability problems that don't work out the way that you think that they should. But this one actually works out to, the way that you think it should. So this will be about 0.9593 if I round to 4 decimal places. All right, so with just one negative test, we aren't super certain. Actually, it's kind of a coin flip. With one negative test, it's just still kind of a coin flip as to whether or not you have the disease. But with two positive tests, it's no longer really a coin flip. There's a very good chance, if you get 2 positive results here, that you actually have that disease. On to number 4, we have a fair coin being flipped. If the flip results in a head, then a marble is selected from an urn containing 6 red, 3 white, and 4 blue marbles. If the flip results in a tail, then a marble is selected from an urn containing 5 red and 7 white marbles. So there's different urns. If the marble selected is white, what is the probability that the flip resulted in heads? So this is a conditional probability. The condition is we end up pulling a white marble. So that's our condition. And they're asking the probability that the flip was a head. So what's the probability of a heads given we pulled a white marble? And we can set up a tree diagram for this. In the first stage of this event, we're flipping a fair coin, so we know the probabilities for heads and tails. There, since this is a fair coin, they each have probability 1/2. Now, if we get a head, then the urn that we're pulling our marble from has 3 different kinds of marbles. It has red marbles, and white marbles, and blue marbles. On the other hand, if we flip a tail, then our urn only has red and white marbles. There's no blue marbles in the tails urn. All right, so the probability, if I flip ahead and I'm pulling out of this first urn, there's 6 red marbles out of a total of, it looks like 13. 6 plus 3 plus 4 is 13. So the probability that I pull a red marble after flipping a heads is 6/13. Similarly, the probability of a white marble after flipping a head is 3/13. And the blue marble would be 4/13. In the second urn, there's 5 red and 7 white marbles. So the probability of flipping a red would be 5 out of a total of 12 marbles. And the probability of pulling a white marble after I flipped a tail is 7/12. Right, now back to the probability that we're interested in. We want to know the probability using our basic conditional probability formula. This is the probability that I flipped a head and pulled a white divided by the probability that we got a white marble. All right, head and white, that would be 1/2 times 3/13, which is 3/26. So that would be our numerator. For a white marble, there's another way we could flip a head and pull a white marble, or we could flip a tail and pull a white marble. So there's 2 different ways to get a white marble. that would be 7 over 24. So when we go to find the probability of the white marble, we got to take our 3 over 26 plus 7 over 24. And I'll leave it to you to do the calculator work on that one, because I'm getting a little bit tired of punching buttons on my calculator. All right, number 5. 1/3 of the employees of a company are women. Women are twice as likely to bring their lunch to work as men. Half of the women bring their lunch. If a randomly selected employee brings lunch to work, what is the probability he is a man? All right, so that last question there, I guess I'll write it down here at the bottom, because that's what we're going to do right at the very end. What is the probability that our employee is a man given that they bring their lunch to work? All right, now, when they told us that 1/3 of the employees of a company are women, that's basically the probability that a randomly selected employee will be a woman. So we're given the probabilities of men and women here. For the probability of our randomly selected employee being a woman is 1/3, and that they're a man is 2/3. And then they either bring their lunch or don't bring their lunch. It says that half of women bring their lunch. So if the person that we select as a woman, there's the probability that they brought their lunch is 1/2, and the probability that they didn't bring their lunch is also 1/2. It also says that women are twice as likely as men, which I guess means that men are half as likely as women. So the probability, if our randomly selected employee is a man, the probability that he brought his lunch will be half of the probability of the woman, 1/4. And the probability that he didn't bring lunch is 3/4. Okay, so there's the main part of our tree. Before we fill it in its entirety, let's go ahead and look and see what pieces we need using our basic conditional probability formula. The probability that our employee is a man given they brought their lunch is the probability that they are a man and brought their lunch divided by the probability that they brought their lunch. So we're just looking at the people who brought their lunch. The women who brought their lunch, let's see, 1/3 times 1/2 is 1/6. So there's a 1 in 6 chance that a randomly selected employee is a woman who brought their lunch, and 2/3 times 1/4 gives a 1/6 chance that a randomly selected employee is a man who brought their lunch. All right, so when we go, the probability that our person is a man who brought their lunch, that's our numerator here, 1/6. The probability that a randomly selected employee brought their lunch, 1/6 plus 1/6. And I don't need my calculator to know that this is 1/2. So again, another slightly unintuitive answer here, since the problem said that men are half as likely to bring their lunch as women. So it seems like if someone brought their lunch, there should be a lower chance of that person being a man. But due to the nature of the workforce in this company, the fact that there's 2 times as many men as women, that kind of cancels out this half as likely business. Is one way to kind of think about this. All right, last problem here, number 6. We have an urn with the first urn has 7 white balls and 5 black balls. A second urn contains 4 white balls and 6 black balls. We're going to pull a ball from the first urn and put it in the second urn, and then I guess shuffle up the second urn and draw a ball from the second urn. We want to know what the probability is that the transfer ball was black given the second ball drawn was black. Okay, so we kind of have a 2-stage stochastic trial thing going on here. We're pulling a ball out of the first urn to transfer. So I'm going to say that this first stage has two outcomes. We transfer a white ball or we transfer a black ball. And looking at the balls in urns, the balls in urn A, let's see, there's 7 white and 5 black, so the probability that I pull a white ball to transfer is 7 out of 12, and the probability that we pull a black ball to transfer is 5 out of 12. And then we're going to put that ball in urn B. Whatever ball we pull out of A, we're going to put that in in urn B. And from urn B, we're either going to pull a white ball or a black ball. I guess I could say this is the second white and the second is black. Or here the second ball is white and here the second is black. Now, if I transfer a white ball from A to B, now B has 5 white balls and 6 black balls. Again, we're looking down this top main branch. We're transferring a white ball from A to B. B already had 4 white and 6 black after transferring the white ball. Now I have 5 white and 6 black. And so the probability that the second ball chosen is white is 5 out of 11. There's now 11 balls in urn B, and 5 of them are white. And the other 6 are black. On the other hand, if I transfer a black ball from A into B, now there are 7 black balls in B and 4 white. 7 black and 4 white, and there are a total of 11 balls. We started with 10 and we added a ball from urn A. All right, so what's the probability that they're asking us for here? The probability that the transferred ball was black given the second ball chosen was black. Using our basic conditional probability formula, that would be the probability that the transferred ball is black and the second ball chosen was black, divided by the probability that the second ball chosen was black. All right, so since I guess our conditional event here is second ball black, we're going to be looking down the branches where the second ball was black. Here we have 7/12 times 6/11, which gives 42 over 132. And on the lower path, our second ball black would be 5/12 times 7/11, which is 35 over 132. And when we grab the pieces that we need, the probability that we transferred a black ball and picked a second ball black, that was the 35 over 132 that we just did. Again, this right here is the probability that both of those things happen. That's what happened down that path. The probability that the second ball was black, we've got two different ways that the second ball can be black, and so if we add them together, 42 over 132 plus 35 over 132, when you simplify this result, you should get 35 over 77. All right, now, hopefully as you were watching, I certainly got sick of it. Hopefully as you were watching, you got sick of hearing me say we're going to use the basic conditional probability formula. We used it in every single one of these problems. Basic conditional probability formula. Basic conditional probability formula. Basic conditional probability formula. Up here, when we found these conditional events, basic conditional probability formula. Basic conditional probability formula. The very first one. There's a conditional probability, basic conditional probability formula. Over and over and over again. All right, so basic conditional probability formula is a big deal. Also, you probably noticed that the strategies here, when we go to find our numerator and denominator for these basic conditional probabilities, it involved finding numbers in this rightmost column. So all of these problems had a very similar flavor. Once you got them set up, I think the challenge here is understanding, getting the information from the story that you need to get the right setup. All right, that'll do it for this video. If you have any questions about any of these problems, please send me a message. If you go to do your homework and find that you have questions about homework problems, please send me a message using the Ask Your Teacher feature in WebAssign.